Hello everyone, thank you so much for joining my talk, and thanks to the Northwest Territories Geological Survey and Nunavut Chamber of Mines for arranging this symposium. Today I'm going to talk about the application of crushing stage test and fluid induction studies on orogenic gold exploration in the Yellowknife Greenstone Belt. First of all, I would like to start with a quick review of orogenic gold deposits. It can be defined as any gold occurrence related with the orogeny and mountain building events. They are quite important since they host over a third of the gold reserves worldwide. Majority of these deposits are found in Archean greenstone belts and Phanerozoic slate belts. They are formed during green schist amphibolite facies metamorphism. Here is a cartoon for the formation of orogenic gold deposits. During this metamorphism, crustal rocks lose their volatiles including water, carbon dioxide, and sulfur, and most importantly their metal content. In the end, a metal-rich metamorphic fluid forms. These fluids rise up through deep crustal faults and deposit at second or third order structures. The two main deposition mechanisms is wall rock sulfidation and phase separation. Generally, in these deposits, gold is in native free form, but as we know from Yellowknife Greenstone Belt, refractory invisible sulfide-hosted gold is also common. The upper figure represents the native free gold and lower figure is the refractory type gold, and both of these pictures are taken from Yellowknife. Depth of formation in these systems is highly variable. It could be epizonal around 3 kilometers, or it could be as deep as 20 kilometers. Formation temperature also varies, but on average it is around 350 degrees Celsius. Orogenic gold exploration could be challenging. One of the major issues is the diversity of mineralization styles. This is the map of the southern part of Yellowknife Greenstone Belt. Gold mineralization in the belt is a great example of orogenic gold. Some of the major deposits and their gold grades are shown. In the Conmine, the mineralization style is mainly native gold and it is more structurally controlled. A few kilometers north, there is Giant Mine where gold is in refractory style and it is believed to be lithologically controlled. To the north, there is Crestorum Mine, again structurally controlled, and to the east, Ptarmigan Mine is believed to be related with both magmatic and metamorphic fluids. I would like to emphasize here that even in few kilometers, there is a variety in mineralization styles. This makes exploration unpredictable and challenging. Another problem with the exploration in vein type deposits is the nugget effect. Gold in these systems are not distributed homogeneously. This means that if you analyze this part of the sample and miss the gold, the ore will be undervalued. For this reason, a proximity indicator for gold that can be performed in the field during preliminary exploration stage could be very useful. A useful gold exploration strategy is to study alteration. However, zoning and alteration in orogenic gold systems are not that prominent compared to porphyry systems. But just like alteration, fluid inclusions are also distributed systematically in hydrothermal mineral deposits. Before explaining this, let me talk a bit about fluid inclusions. The definition is, fluid inclusions are small pockets of fluid trapped in a mineral during crystal growth or healing of a fracture. Most importantly, they can represent small samples of the fluid carrying precious metals. Fluid inclusions could be as simple as a liquid and vapor, or they could be a complex mixture of solids, vapor, and liquid. Here is a cartoon of a porphyry system. Fluid inclusions are also systematically distributed similar to alteration. For example, at the core of the system there would be dominantly melt inclusions. In the shallower parts, aqueous fluids exhaled from the melt are more dominant. Presence of brine and vapor together may suggest a horizon of unmixing. Distal fluids would have lower temperatures and hence smaller bubbles. This type of study is very useful to understand which part of the system you are in. Distribution of fluid inclusions are also systematic in orogenic gold deposits. A previous study has shown that high pressure volatiles in fluid inclusions correlate with elevated gold values. In this figure, we are seeing an auriferous quartz vein and tonalite wall rock. The results show that as you get closer to the quartz and the gold, gradually volatile content increase. In this case, volatiles were carbon dioxide. In our study, we followed a similar strategy and we tried to find if high-pressured volatiles is a good proxy for gold mineralization at the Yellowknife Greenstone Belt. Very briefly, I want to talk about the geology of the study area. We are looking at the southern part of the Slave Craton. Archean-aged Yellowknife Greenstone Belt is approximately located over here. The rectangular area is where our study is focused on. This belt hosts world-class giant and cone mines with over 13 million ounces of gold production. Also, diversity in mineralization styles and host rock lithologies provides a good example for orogenic gold mineralization. Here is the stratigraphic column of the belt. Very simply, Chem group represents the mafic volcanic rocks, Banting group is more felsic to intermediate volcanic rocks, and Burwash formation is a thick turbidite sequence. In many cases, these rocks are intruded by the defeat plutonic suite, and it is known that gold can be hosted in any of these lithologies. Some of the characteristics of orogenic gold fluids are they are low salinity, aqueous carbon dioxide rich fluids. Probably very characteristic of an orogenic gold is their volatile content. Typically, they are very rich in carbon dioxide, but minor amounts of methane and nitrogen and trace amounts of hydrogen is also present. Here in these two figures, we are seeing the most common inclusion type. In the upper figure, there is carbon dioxide gas, carbon dioxide liquids, and water. This type of inclusions implies high gas percentage. Lower figure is a single gas phase inclusions and most probably consist of high pressure carbon dioxide. In this figure, we are seeing the principle of the fluid inclusion crushing technique. Compressed volatiles within the fluid inclusions is liberated by the crushing the host mineral. Since they have high pressure, once they are exposed to the lower atmospheric pressure, they will expand and form a big bubble in an insoluble oil. We can use this principle and assess the volatile content of a sample. Crushing stage test, which you can see in this figure, is a very practical test that can even be used in the field. Basically, you will put a small grain of quartz between two glass slides and cover it with an immersion medium in which volatiles are insoluble. Then you will put the glass and the sample over here. With this screw, you will gradually crush that grain. With a microscope or even with a hand lens, you can observe through this aperture. This is the result of a positive crushing test, which means the sample is rich in volatiles. This is the original picture of the quartz grain. As the grain is crushed, volatiles in it migrate and liberate. After escaping the rock, they expand and form bubbles. We believe that crushing stage test results could be very valuable at the early stage of exploration, especially when there are many samples and you need to narrow it down. We use this test on samples from the Quyta-Bell property. This part of the belt is the least explored area, but the presence of gold is known from historic Clan Lake and Mon mines. Mineralization can be characterized by native gold occurrences within quartz veins, and there is a variety in host rocks including mafic to felsic metavolcanics and metaturbidite rocks. We use this test on 25 samples prior to knowing their gold content. Based on our observations, we give a score to each sample. A score of 1 means no volatiles, and a score of 3 is a volatile-rich sample, and score of 2 is the intermediate. In this graph, x-axis represents the gold values in logarithmic scale. In this study, we considered a sample auriferous if it has more than 0.2 ppm gold in it, which is represented by this red line. Y-axis is the crushing test score. 1 corresponds to no volatiles and 3 corresponds to volatile-rich sample. 5 out of 25 samples have gold in it, and we successfully detected 80% of the auriferous samples. Among the barren samples, we identified 4 false positive tests, which means volatile-rich but no gold. We successfully discarded the other 75% of the barren samples. The biggest issue was this false negative test of sample 63, which has gold in it but no volatiles. We believe that 4 false positive tests might have been caused by the nugget effect, but our results could still be used as a proxy for gold, and these 4 samples should be focused more. I also would like to talk about the 1 false negative test. We should not forget that this test must be applied to orogenic type mineralization only, and different types of mineralizations are also present in the Yellowknife greenstone belt. As it can be seen in this figure, texturally this sample is very distinct from other samples, which could be as a result of a different gold mineralization. Next step of this study is to look into these fluid inclusions in more detail. Fluid inclusion petrography revealed that results of our crushing test correlate with specific fluid inclusion types. Type 1 inclusions, which are low salinity aqueous inclusions, are most common in barren samples and negative crushing results. On the other hand, type 2A inclusions are single-phased, gas-rich inclusions that correlate with gold and positive crushing test results. In a small number of samples, we also recognize these two-phase vapor-dominated inclusions. They are dominant in texturally anomalous auriferous samples. Here is the tabulated version of our results. As I have mentioned before, vapor fluid inclusions, which are type 2A, are always present in positive test samples and in gold-bearing samples. Other than type 1 and 2 inclusions, in smaller amounts, fluid inclusions with high salinity and carbon dioxide-rich aqueous carbonic inclusions are also present. In most cases, these saline inclusions are found in fractures as late fluids. Another interesting observation we made was the presence of dark-colored solid inclusions. In most cases, these type of inclusions are closely associated with vapor-rich type 2A inclusions. These inclusions are also very common in gold-bearing and positive test samples. Raman spectroscopy is an instrument that is widely used in fluid inclusion studies. To describe it simply, you shoot a laser into a sample, and based on the vibration between the atoms, you record a signal back. This signal looks like this. Raman shift in the x-axis is unique for different chemical bonds. In this example, we are seeing peaks for carbon dioxide. One of the advantages of this instrument is its resolution. We can use it on fluid inclusions as small as 5 micron and still get reliable results. We use this technique to identify the volatiles in each sample. And as expected, the most common volatile is carbon dioxide in our samples. Here is another result, and in this case we are seeing the peak for methane. After carbon dioxide, minor amounts of methane is also present. In most cases, they are together with carbon dioxide, but in this case, it is pure methane inclusion. This is where it gets interesting. So far, presence of both carbon dioxide and methane are very common in orogenic gold systems. A couple of slides back, I have showed you some dark-colored solid inclusions. We used Raman to identify them, and we found out that they are graphite. Here in this figure, you are seeing the Raman result of this spot, and this signal is very typical of a graphite. And here is the Raman analysis of the gas bubble. In many cases, graphite is present with carbon dioxide, as it can be seen from this figure. Graphite can also be found with methane or with a mixture of methane, carbon dioxide, and graphite. This inclusion is one of the best examples, because all of the volatiles identified in our samples could be seen in this inclusion. We can see the peak for carbon dioxide, for graphite, some nitrogen, and methane. This table shows the results of Raman analysis. Most common components in our samples are carbon dioxide, followed by graphite and methane in decreasing order. Minor amounts of nitrogen is also found in one of the samples. We tried analyzing inclusions in sample 63, but we couldn't detect any volatile other than water. It is safe to say that both carbon dioxide and graphite is in good correlation with gold-bearing samples. To conclude, results of the crushing tests show that they can be used as indicator of proximity to orogenic gold mineralization. This test will be most beneficial during the preliminary stage of exploration, especially when there are lots of samples and you need to narrow it down. It is very easy to do it, and it takes no more than 2 or 3 minutes per analysis. Perhaps the biggest advantage is you can even do it in field conditions and gather some valuable results. We found out that vapor single-phase inclusions are the higher pressure volatiles detected in positive crushing tests. In many cases, these are either pure carbon dioxide or a mixture of carbon dioxide and methane. We tried to find a systematic distribution between volatiles and gold. Our results suggest that carbon dioxide and graphite, with or without methane, seems to be present in all of the gold-bearing samples. Of course, this project is not finished yet, and as we analyze more samples, we will be more confident to suggest this correlation. Thank you for listening to me, and I want to thank everyone again organizing this event. I would be happy to answer any question related with my project.